up, Calc students? Let's do critical points. Unit 3, human graphing calculators. Homework 1, critical points mean value theorem. What is a critical point? It's when our slope of our function equals 0 or it's undefined. What are we finding? We are finding possible max min locations. What's really going to be interesting about this unit 3 is we are going to try to eventually graph a function, but we will find that to graph a function or to understand a function's shape, we should be looking at its slopes, because slopes tell us how things are changing. And if you understand how things are changing, you understand the original function. So we are going to look at derivatives, slope equations, and we will be analyzing slope equations. So we want a nice slope equation. We want it factored if at all possible, so we can find said zeros or times when it's undefined. And for right now, all we're going to do is just say these are possible max min locations. These are our critical points of F. Cool? Sometimes we'll have more than one. Sometimes we'll just have one. Sometimes we'll have none. I'm ignoring the undefined part because we know undefineds are when we have a denominator that has a 0 in it. I do not see a denominator, so I don't have to worry about the undefineds. But we're really just taking derivatives, getting slope equations, and then the rest of this unit we will be like, hey, how can we analyze the slope equation to help know things about the function better? And we will start by finding when our slopes equal 0 or undefined. I don't have to pay attention to that. We'll find we will be factoring a lot. We will factor correctly. Don't make the mistake that if you factor out a number, you include you include 0 as a solution. If I use commas, just know that means there are two x coordinates where we have possible max mins. That's not a point or anything. Don't forget all your derivative rules. If you have x to the fourth over 4, you don't use the quotient rule. You just write it as 1/4 x to the fourth. Constants stick around unless they're by themselves. The 4 comes down, gets multiplied by 1/4, and is a 1, so I get x cubed. This would be written as 5/3 x cubed. The 3 comes down, multiplies by the 5/3, and it becomes 5x squared. 2 comes down, becomes 6x. I would factor out an x. I get x squared plus 5x minus 6. I would see when this is 0, I can ignore the undefined. I would factor this to be x plus 6, x minus 1. And I get x equals 0, x equals negative 6, x equals 1. Cool. With trig functions, you just got to remember your derivative rules and then use them the correct way. Here I would get cosine x minus sine x equals 0. Good technique to solve this is to get one trig function on one side, the other on the other. I'm going to add sine x, divide by cosine x to get 1 equals tangent x. Tan equals 1 at the pi over 4s in the first and the third quadrant. So I need to find the pi over 4 in the first and the third. That's going to be at 1 pi over 4 and 5 pi over 4. Need to boost my battery. Cool. Quotient rule. Don't forget about the quotient rule. Slopes of the top times the bottom. Minus the slopes of the bottom times the top. All over. Bottom squared. Now we have a denominator. We have a slope equation that has a numerator and the denominator. We got to set both the top and the bottom equal to 0. Top equals 0 is when our slopes will equal 0. Bottom equals 0 when our slopes are undefined. Cool. So we got to simplify. I got 4x squared plus 4 minus 8x squared over x squared plus 1 squared. I'm not going to simplify that. I get negative 4x squared plus 4 over x squared plus 1 squared. I can solve this equation set equal to 0. Subtract 4 divided by negative 4, I get 1, which means x equals plus or minus 1. The bottom equation, though, x squared plus 1 equals 0, gives us x squared equals negative 1, gives us no real solution. So we would actually not have any times when the denominator equals 0. Making a homework video, Brooks. Yeah.
My photo's at 8:15. What time did you meet?
I'm at 7:45.
Perfect. See that? I'll be in my suit too, so I'll be looking extra professional.
I love it.
All right.
No shout outs for Luke?
I know. He was like, I showed him the slide, and he was like, oh no, I get it. Okay, nice. He understood.
We got x to the 1/2 minus 1/3 x. We will take the slopes of x to the 1/2, and we have 1/2 x to the negative 1/2. And then the 1/3 x turns into 1/3. Now, for purposes of our future, again, we are going to be analyzing the slope equation. And knowing about the slope equation will help us know about f. So we really want a simplified slope equation. So usually we would if told to set something equal to 0 and solve, you would just add the 1/3 over and stuff like that. But actually, for purposes of your future in this unit, I actually want you to combine these two things into one nice fraction, where we have just one numerator divided by one denominator. I want you to smush these two fractions together. Now, the way we could do this is by getting a common denominator. We're going to multiply both fractions by each other's denominator to get 3 minus 2 root x over 6 root x. This is a nice simplified slope equation. Okay? And we want to see when this is 0. We want to see when this is undefined. We will look at the top equals 0 and the bottom equals 0. Square root x equals 3/2, x equals 9/4. We don't worry about pluses or minuses when we're squaring to solve an equation, but when we square root to solve an equation, we need a plus or minus. That's an example of a problem, guys, that if you didn't get right, you do again on your own. Okay? This problem. If you don't get right, do it again on your own. So before I'm even going to set this equal to 0, I'm going to make it one nice fraction. It's just too hot. It's too hot. It's too hot to have ACL. I hate hot ACL. I don't hate hot ACL. I always have fun at ACL regardless. However, when it's hot, it just doesn't make it as fun. People are a lot more cranky. My kids are not coming this weekend. They're coming Sunday and they're coming next weekend. It's too hot. It needs to be later in October. It's just too hot in Texas in early October. All right, I digress. X equals 0.
So I thought it was like only gonna fall down there.
X to 1/3 equals negative 1/3. I'm going to cube both sides. I get x equals negative 1/27. You cube negative 1/3, negative 1/3 times negative 1/3 times negative 1/3 is negative 1/27. Make sure you know how to do that. Make sure you know how to solve an equation. X2 plus 6, x to 1/3 equals 0. Okay? Great. Moving on to the mean value theorem. It's a theorem that we're actually familiar with, at least what it means. Mean value theorem guarantees that there is a x location where the instantaneous rate of change equals the average rate of change over an interval. So instantaneous rate of change is the slope of a function at a point. The average rate of change is the slope over an interval. Cool. The function needs to be differentiable for us to invoke the mean value theorem that guarantees that we have a tangent slope equal to the secant slope. A function is twice differentiable. Just means you can take the derivative twice, which means you can take the derivative, which means it's differentiable, which means you're good. Whenever you read twice differentiable, just know that it means like you can take the derivative twice, which means it's very smooth. If f of 3 equals 8 and f of 5 equals negative 5, well, we can see our y change is minus 3 and our x change is plus 2. We are guaranteed to have some tangent slope at some x value that equals this secant slope. And our x value is guaranteed to exist somewhere between 3 and 5, which are our x coordinates there. Okay? So this is the purpose, and this is what we did last unit. Now it's just a little bit more formalized. Find the value guaranteed by the mean value theorem. So you're like, mean value theorem, what's that? It's the whole slope at an x value equaling your slope over an interval. To find the slope over your interval, you need your y coordinates. You need your change in your y over your change in your x. You got 4 minus negative 6 plus 2, so that's 10, 11, 12. We got 9 minus 9 plus 2, that's 2. 12 to 2 is a minus 10 change. Negative 2 to 3 is a plus 5 change. Slope, y2 over y1, x2 over x1 is negative 10 over 5. The average rate of change is negative 2. The slope at x is 2x minus 3. The x value is a half. Solve that equation. That x value is guaranteed. That x value is in between negative 2 and 3. Okay, cool. So we just do the average rate of change over your interval. And we find our slope at x. That's the slope equation of the original function. This is the slope at x equal to the slope over the interval. Average rate of change, use the slope formula. Slopes of tangents, you don't have a calculator, so you have to use the slope equation. F of 1 is negative 4. F of 3 is 27 minus 15, which is 12. From negative 4 to 12, that's a plus 16. From 1 to 3, that's plus 2. So, when will my slope at x equal my slope over my interval? I believe this is the exact same question as your test. Now, you say plus or minus root 13 thirds, but just like on your test, you notice that there was only the positive root 13 thirds, because that's the only value guaranteed on your interval by the mean value theorem. Cool? Sometimes you're asked to visualize the mean value theorem. So, draw your understanding of the mean value theorem. Again, the mean value theorem says there is a slope at an x value that equals your slope over your interval. The slope at a point, slope over your x interval. Slope at x is a tangent slope. Slope over an interval is a secant slope. Great. From -2 to 5. There's the y's. This is the visualization of the secant line. The slope is the average rate of change. For slopes to equal each other, you need to create parallel lines. I would say probably right around here, we can see a tangent slope that is parallel to / equal to the secant slope. My friends, this is the visualization of the mean value theorem. You sketch your average rate of change, which is your slope over an interval. You sketch your slope at a point that is equal to or parallel to the slope over your interval. From -4, that'd be this y-coordinate, to 3, that'd be this y-coordinate, I can see this slope, oh, that's bad. Is the slope of the secant. This is the slope that equals the average rate of change of the function. And I would say that here is one location where the tangent slope and the secant slope are the same. But there's also another location. The mean value theorem guarantees there's at least one. You might have two. You might have 200. Who knows? Guaranteed to exist and occur. All right, let me finish off with analyzing characteristics of graphs. Now, again, this is just the graph. Okay? And this graph, I don't really care about like the y values of the graph, because we are looking for x values or x intervals. We are told the graph has a point of inflection at x equals 1. Might not have talked about points of inflection. The points of inflection where curvature changes. All right, so we could see curving down. We would call this portion of the graph concave down. I like to go CC down. Curving up is concave up. All right? Now, look at the first two questions. When is this graph negative? And then when are the slopes of the graph negative? Those are two different things. The graph is negative when the y values are below 0, or when we are below the x-axis. That's going to be from -infinity to -2, and then from 0 to 6. Cool? But the slopes of the graph being negative are when the slopes are negative. Well, we'll talk about how if slopes are negative, the function is decreasing. We already know that, but we'll talk more about how knowing the slopes tells you how your function is changing. Now the graph is increasing. Well, the graph is increasing when the slopes are positive. You can see from -infinity to -1 and from 4 to infinity. The graph is concave down from -infinity to 1. The graph is 0. It equals 0 at -2, 0, and 6. But the slopes of the graph are 0 at -1 and 4. Very, very important in this class to understand when graphs are increasing, decreasing, when graphs are positive, when graphs are negative, when graphs are equal to 0, and when graphs are having slopes of 0, because in the future, we will be looking at a graph and then being like, ooh, I should be looking at these characteristics of this graph. And that will help me understand answers to questions that we have. All right, we have a point of inflection at -1 and a point of inflection at 2. So this is where our curvature is going to change. When is this graph 0? The graph equals 0 at x equals -3 and x equals 0. I can see a 0 at 0. And x equals 6. Now the slopes are 0 at -2, 0, and 4, which is interesting because the slope is 0 when the graph is 0. Not always the case. The graph is negative to the outside. The graph is increasing when it's going up from left to right, so that's negative infinity to negative 2. That's 0 to 4. The slopes of the graph are positive. The slopes of the graph are positive. Oh, it's the exact same answer. It's a very important distinction. That slopes being positive means the graph is increasing. The graph is concave up. Between our two inflection points, negative 1 and 2, we can see we're frowning up there. Point of inflection at 3. X values are intervals. The graph is negative. The graph has negative y values from negative 1 to 2 and from 6 to infinity. The slopes are negative. Slopes are negative when the graph is going down, decreasing, negative infinity to 0 and from 4 to infinity. The graph is 0, negative 1, 2, and 6. The slopes are 0 at 0 and 4. The graph is curving upward from negative infinity to 3. The graph is going down when its slopes are negative. Negative infinity to 0 and 4 to infinity is actually the same answer to these two questions. The graph is going down. The graph is going down. Okay? I don't know if you can see these answers because my face is in the way. There you go. All right. See you at ACL. Peace.